Hey guys, this is Cole Taken. Today I'm doing a topic of fluorescence, resonance, energy transfer, and this is going to be my presentation. So the background, introduction, and principal techniques. We're just going to talk a little bit about fluorescence, resonance, energy transfer. FRET is also known as Forster Resonance Energy Transfer. It's named after the guy who kind of like first started it, made it, I guess you could say. It refers to the non-radiative transfer of energy from an excited donor fluorescent molecule to an acceptor molecule. So from a donor protein to an acceptor protein. Applications of FRET are numerous, but FRET was used to create biosensors of ions or the active state of a protein, measure protein proximities, and measure changes in organization or composition of a protein complex. So as you see, FRET is used for a lot of things. It's very useful. It's big in the cell bio field also. Let's go to the next one. How it works is the usage of FRET is commonly two fluorescent proteins in close proximity, where there's a donor and an acceptor. The donor protein will absorb a photon, exciting the donor, going from ground state to a higher state of configuration. The configuration will then drop, transferring energy to the acceptor protein, who will then get excited and emit a photon. So once this donor protein gets a excitation in it, it'll jump the configuration, and once it comes back down, it starts transferring this energy to the other protein that's pretty close by. And we'll see how that works in the next slide. Energy efficiency would be then calculated with all the correct components. So there's a formula that's actually used for energy efficiency, inverse to the sixth. It's just Forster's distance and stuff like that. I didn't know if it was necessary for this presentation. Experimental research using FRET, using proteins CFP and Venus. They're both fluorescent proteins. They're good for experiments like this, but in my research article chosen, using figure 1, the question asked, why is spectral overlap and distance under 10 nanometers and correct orientation important? It is very important. 3 different designs were set up, such as spectral overlap versus no spectral overlap. As you see on A over there to the right a little bit, this top side. And then over here on B, we have the distance where it's under 10 and over 10, showing that it's not being emitted anymore once it's further than 10. And then C, we have the correct orientation versus the wrong orientation. So this figure is showing that there's 3 questions being posed and the photon being emitted if requirements were correct. The figure shows spectral overlap is required, proximity distance under 10 nanometers is required, and morphology of proteins need to be similar. So as you see in A, they need to have some kind of overlap for FRET to occur, and that's called a spectral overlap. And then in B, you see that the distance for the first one is over 10 nanometers, and the CFP won't transfer that energy over to Venus, so it'll just emit its own photon. And then if you see when it's under 10, it'll actually transfer that energy to Venus, which is the FRET, and then it'll emit that photon at a higher nanometers wavelength. And then C, when it's in the correct orientation, it still emits it, but when it's the wrong morphology, it'll not go through and the energy will not be transferred as supposed to. But overall, this was the main part of the experiment, that just making sure you understand the basis of how fluorescence, resonance, energy transfer works. It's really important to have these 3 things. You need to have them. You need to have them like this in order for the energy to be transferred in the other protein to emit the photon. What if one of the proteins do not exhibit fluorescent characteristics? That's a question for you guys. Get back to me on that and let me know how that goes. And these are my references, and that's pretty much my presentation. Thank you.